Hey there. Let's get started on some examples. So last video we learned about why, how, and why. This technique of solving linear first order differential equations works, but we didn't do a whole lot of examples. Now I'm going to start going through some examples. So you may be able to skip through some of these. I would recommend you watch all of them and then see that you know how to do them on your own. That's a great study technique. See if you can do them without your notes. If you can, awesome. Go ahead and move on. If not, let's go through a lot of these pretty slowly for some of them. We're going to start building up the intensity as we move towards the end of the video. So right now it's all about learning what in the world we're doing. So there's a few things I want you to check every time we go through one of these equations. Number one, does it fit the technique you're trying to use? If it does, awesome. If it doesn't, can you make it fit? Or if it doesn't, is there an easier way to go about it? So if you're struggling to make it fit a technique, maybe there's a different way. So number one, does it fit the technique that you got? If it does, cool. If not, make it fit. Or if it doesn't make it fit, use a different technique. So let's check this out. Does this fit separable equations? Not even close. No, it's got x's floating around. We're not, even if we subtract, there's no way to factor anything, get our y over. So this is not separable. This is linear though. So does it fit linear? We got a derivative, it's a first derivative. We have some function times y, and we have no other y. So we have y to the first power. It's already grouped with the dy dx. So this is what we're looking for. We want a first derivative based on y. We want added or subtracted to some other term where you have a y in it. X's can be there or not, it doesn't matter. But then that y is to the first power, there's no other y's, and there's only at most x's on the right-hand side. So this is exactly how we want these structured. Let's go ahead and let's solve it. Remember the idea, you needed to watch the last video. The idea is you're going to try to complete a product rule. You're going to try to complete the result of a product rule. How to do that was to realize that you need something that repeats. That would be e to the function of x, and the derivative of the function of x has to be this piece. If you didn't watch the video, you need to go watch that right now to make sure you understand the concept, because I'm not going to reteach it. So the plan was, let's multiply by that missing piece. To get this structured this way, we would have had to divide to get it structured this way. So we're going to multiply to undo that. What we multiply by is e, because of e to some function repeats itself when we do a product rule. E to some function whose derivative is the thing that's connected to our y, that function of x, or constant in this case. So if the derivative of this piece needs to give us 3, the integral of 3 needs to be that exponent. Whenever we do these, I would start also and write down what our p of x is. So we first thing we check, hey, does it fit the format of being linear? Yeah, it does. What is p of x? P of x is the piece, the coefficient or function of x that's connected to your y variable first power. In this case, it's just 3. That is the piece you're going to be integrating every time. So you're always integrating a 3 because the derivative of that antiderivative needs to give you back 3 when you take the derivative of the exponential. So in our case, our rho of x is e to the 3x. Done. That is the piece that when we multiply is going to complete our product rule. That's pretty cool. You don't need a plus c here. We talked about y in the last video. All we need to understand is that you're going to do that e to the 3x times dy dx. Because you're multiplying both sides, it's also going to be multiplied to the middle term and to the right term. Now you're going to see this a lot. A lot of times things start simplifying. You go, who in the world would put e to the negative 3? Who would put e to the negative 3x in a problem? You go, yeah. In the last video we learned that these are coming from when you divide by something. Look at this. If you divide by e to the 3x, you are going to get that e to the negative 3x. We're multiplying to undo that, which is pretty cool. So we found out that our p of x is 3. Doing the integral of 3 gives us 3x. Why do I do that? I need to be able to take the derivative of this thing, get it back in both places, and have the derivative of my exponent be that number right there. That is what would complete our product rule for us. So we simplify, and you're going to see that this does this a lot. This is going to simplify a lot of stuff here. So we have that completely gone. E to the 3x, e to the negative 3x, you add exponents, you get 0. E to the 0 is 1. So on the right-hand side, we just get 2x. On the left-hand side, this is the time when you want to check your work. You want to check that when you take a derivative of your exponent, the derivative of this piece is that number, or that expression, or that whatever that is. Because this has to be the derivative of this piece. It's got to match up. Remember how product rules work. You leave it alone one time, you take the derivative in the other term. That's happening. That's what's going on. So we have e to the 3x dy dx plus 3e to the 3x times y. And then we're understanding what in the world happened. You see, this can look confusing. If you don't understand that this is the result of a product rule, you're going to go down a rabbit trail and go, I have no idea what I'm doing here. This is the result of a product rule. How product rules work, remember, it's a result of an implicit derivative with respect to x. So it says when you take a derivative with respect to x of this product, it has to give you back this thing. What's the product have to be? When you take the derivative of a product, you leave the first term alone, first factor alone, I would say. First factor alone, that's the first factor then. You take the derivative of that first factor, that is the derivative, but then you have the derivative of the second factor, and you leave the second factor alone. So to build your product, all you have to do is look at this and go, hey, this piece right here, this would not have a derivative. This would not be a derivative. You would not be taking the derivative to get this piece, because this is the derivative of the second piece. Remember how product rules work. Leave the first one alone, derivative of the second. That's the first one alone. Then you take the derivative of the first one, you leave the second one alone. That's the second one. We haven't done hardly any calculus right now. We haven't done an integral. All we've done is said, because I multiplied by the missing piece, the appropriate term, the appropriate factor, rho of x, I now have this as the result of some product rule here. How do you undo the derivative, the product rule? An integral undoes it. So we're just going to integrate both sides. With respect to what? Well, since that's a derivative with respect to x as an independent variable, we're going to integrate with respect to x. Now, since we have an equation, we do it on both sides. Integrals and derivatives undo each other. We get e to the 3x times y equals x squared plus c. We talked about why we don't need a plus c when we're doing this integral. We talked about why we don't need a plus c on this one, and why we do here. If we had a plus c from this integral, we would just add or subtract it and get a different plus c. It doesn't really matter. Now, we can solve for, and I would do it right now, I'd solve for c now if I had an initial value. I'm not given that, but here's where I would do it. Instead, let's just solve for y whenever we're able to. If I solve for y, we would get x squared plus c, and then e to the negative 3x. And the reason why we get e to the negative 3x is we divide both sides by e to the 3x, or multiply both sides by e to the negative 3x there. And you're done. That's as much as we can do. So the idea is, I hope it's making sense, that we're trying to structure this as the result of some product rule, then to find the product. It's so nice because each term has a factor in it that comes from our original product. Just find that factor. It's always going to be the function of x that's before the derivative of y, because the y is what you would have taken the derivative of here, times y itself, because this is not the derivative of y. Put it together. Then integrate both sides. Let's go ahead and move on. So first things first, does it fit the technique we're trying to use? Well, it's not separable. It looks linear to me. Let's double check. I've got a derivative of y minus some function of x times y itself to the first power, and then no other y's anywhere else. So that's linear. Now, can we write out what the pieces are that are necessary for us to understand? Let's try to write out p of x. P of x is the piece that when I take the derivative of the exponential I'm about to get, I'm going to get p of x. So p of x is the thing we want to integrate to find our exponent. P of x is always the function of x in front of y with the sign. So p of x would be considered as negative 2x here. Let's find the piece that's going to complete our product rule. Well, we know that product rules normally have something in front here, so we're going to be multiplying. We also know that if I'm multiplying in all three places, because I got to multiply both sides here, that derivative needs to repeat. So the function itself and the derivative of the function need to have the same thing in it. That's creating an exponential idea. The exponential also, as I just mentioned, needs to be the case that when I take the derivative of the exponent, it gives me negative 2x. Okay, find the integral of negative 2x. That way when you take the derivative of it, it gives you 2x. That means that our rho of x is e to the, well, we can pull the negative out and get x squared, so negative x squared. Don't need a plus c. That's what we're going to be multiplying our differential equation by, all three terms. So both sides, all three terms. That means that we'll have, let's see. It doesn't matter what side you multiply on since multiplication is commutative. So when we multiply, don't worry about where you're putting this. I would just multiply and make sure you're doing all three of them though. E to the negative x squared, okay. E to the negative x squared, no problem. E to the negative x squared. Don't forget the right-hand side. And just stop for a second. Just double check. Just look at this one place. Is the derivative of that exponent equal to the pieces of x that you have? If it is, you're good to go. So derivative of negative x squared is negative 2x. Hey, there's negative 2x. You're done. That's fine. Simplify the rest of it, sure. So e to the negative x squared dy dx minus 2xy e to the negative x squared equals, that's 1. E to the x squared times e to the negative x squared gives you 0. That's 1. And then we are going to do two steps here. We're always going to show this. So there's a few things we always do. We always show what p of x is. We always show what rho of x is. So just the integral of this, no problem, and put it as an exponential. We always show what we're multiplying by. We always show our simplification. And then we always show that this is the result of a product rule. So you're going to show that this was the result of some sort of derivative. The result of some sort of derivative with respect to x of some sort of product. We don't jump down here and just solve it all the way and go, well, yeah, this comes from the product itself, and I do the integral. We don't really do that. This shows your understanding that this is the derivative with respect to x, so that's implicitly, as y is a function of x, of some sort of a product. And then to undo that, that's where your integral comes from. To show it in one big step sort of loses the technique. It sort of loses here's the math behind it. I don't want that for you. I want you to show the math behind it. So the product itself says, if this was the derivative of the second factor, this is the original first factor itself. If this is the derivative of the first factor, this negative 2x e to the negative x squared, then that y is the second factor itself. So most of the time the textbook will just tell you this is always going to be that. It's always going to be rho of x times y. That's true. And you can do math that way and not understand how to look about it. But the reason why this is because this piece would be the piece when you take a product rule that you're not taking a derivative of. That means it's got to be your first factor. This piece is a derivative of your x stuff with the exception of the y. The y here is not the result of that derivative. It's the piece of the product rule that you're not touching with the derivative. That's why we can change this into that nice product. That's why, and that's why that's just rho of x, because of that idea. On the right-hand side, we just get 1, and now is the time where you say, oh yeah, okay, so if this is the result of a derivative, let's just integrate to get rid of the derivative. Integrate with respect to x because it's a derivative with respect to x. Derivatives and integrals are an inverse idea. They undo each other. Fundamental theorem of calculus tells us that we're going to get e to the negative x squared times y equals just x plus c. Yeah, we need a plus c. And if we multiply both sides by e to the positive x squared, then we're going to get y equals x plus c and then e to the positive x squared. And we're good. That's the idea behind it. Let's go ahead and we'll try that last one. You'll notice that this is just a little bit different because we got an initial condition up there, but the idea is the same in that we want to see that it fits our technique. We want to use the technique appropriately. We want to show some really pertinent stuff here. So let's first check to see if it fits the technique. That was great. That was great. This is not so great. So right now, this doesn't fit the format of being linear. Can you see why? Can you see why that doesn't fit? It's really close, but we know that we want just dy dx plus or minus some stuff that has a y to the first power equals some stuff that is only in x's. The problem here is that x. Do not write down p of x. I do want you to write down p of x, but do not write down p of x right now. You need to put it in the correct form first. So we think form before we do anything else. Does this fit the form? The answer is no. We need to make it fit a linear function, a linear first order differential equation if we're going to do this technique. What that means is you might have to multiply or divide to make it fit. That's not a big deal. Just make sure you do it before you start finding p. Because if you find p now and you say, oh, it's 5, and then you integrate that and you go, oh, it's 5x, and you e to the 5x, it's not going to work. This is not going to work for you. So we need to make sure it's the right form. That way when we integrate the p of x and put e to that function, it's giving us back the original function itself in terms of x, and then the derivative of the exponent would be our p. That's not the case right now. So let's divide everything by x. So we'll at least have a dy dx. That looks better already. Plus, when you write out that second term, this should always just be dy dx. The second term needs to be a function of x times y. So when we write this, a lot of times we make it a fraction times y like that. You don't have to put the dot, but I'm just trying to show you that I don't want this all wrapped up in one fraction. I want 5 over x to be the thing, the p of x you're talking about. On the right-hand side, feel free to simplify that. That's just 7x. Now that's linear. Now it looks better. Now it's something I could say, yeah, my p of x is 5 over x. Can I find the missing piece, the thing that when I multiply all 3 terms by it to complete my product rule, it's going to repeat when I have the function itself and when I take a derivative of that function. More than that, when I take the derivative of the exponent, it's going to give me this. When I take the derivative of the exponent, it's going to give me this. When I take the derivative of an integral, of that 5 over x, it's going to give me 5 over x. That's how we're finding our row. Row of x is the e to the x gives you back when you have the function itself and the derivative of the function. And then when I take the integral of 5 over x, that gives me something that when I take a derivative of it, gives me p of x, gives me 5 over x back. So that's e to the 5 you pull out, 1 over x is ln x, so that would be 5 ln x. If we move our exponent up, that's e to the ln of x to the 5th. This happens frequently that you'll have e to the ln, and you go, well, don't those simplify? Yeah, they sure do. We just get x to the 5th power. That is what we're going to multiply right now. So when we multiply every single term, both sides means distribution, both sides means every single term, then that row of x, that's going to be the piece that when we multiply this through, that's the piece that we, when we did a product rule, didn't get a derivative taken. Because the derivative of y would give us dy dx. That means the other piece that came from a product rule didn't get touched with the derivative. So I have my original dy dx, 5 over x times y, 5 over x times y, 7x, 7x, and I've multiplied every single term, that's both sides distributed, by x to the 5th, that's rho of x. Let's simplify what we can. 5x to the 4th. We don't have to worry about the right-hand side hardly at all. We're only trying to make the left-hand side into that product rule. Let's see if it worked. What we need to be able to do is think about, is the derivative of this giving us all the x's right here? The derivative of x to the 5th gives us 5x to the 4th. That works. That creates this result of a product rule. We're just going to write it. So what do you need to take the derivative of with respect to x to get this? We need to take the derivative of some sort of a product, since that's the result of a product rule. How we do a product rule is we leave the first factor alone. Therefore, that's got to be the first factor. We take the derivative of the second factor. Okay, this has got to be the derivative of the second factor. That's y. Then we take the derivative of the first factor. Okay, this has to be the derivative here. Check it. Make sure that it is. Okay, cool, good. And then we leave the second factor alone. That's got to be the second factor that gave us that as a result of the product rule. That's how this works. On the right-hand side, 7x with 6, no problem. If we integrate both sides with respect to x, because you took this as a derivative with respect to x to get that product rule to work for you, there's no work that has to happen besides your understanding of calculus in that integrals undo derivatives. That means that x to the 5th times y derivatives are undone by integrals and vice versa. On the right-hand side, we would get x to the 7th plus c. Plus c. Right now would be a good time to solve for c. Remember with those ln's, we want to kind of get rid of that, wrap up the e to the c plus and minus in a bigger plus c, and then use our initial value or initial condition. Here, it's easier to solve for c the way it is. So we're going to go ahead and do that. Man, why did I pick those numbers? It's crazy. So if I plug in 2 for x, and 5 for y. So we plug it in. If we take 2 to the 5th power times 5, subtract off 2 to the 7th power, we get c equals 32. Let's just put that back in there. So we have x to the 5th times y equals x to the 7th plus 32, and we're just going to divide by x to the 5th. Done. That's the idea. Make it fit, or maybe a different technique. Let's see if you can make it fit fairly easily to a technique you're trying to use, in this case linear. We'd have to divide, and then we're just finding the missing piece that creates our product rule. That's pretty much about it. We have lots more examples, so hang on. So let's go through and try a few more. Again, we're going to try to see that this is going to fit linear. Then we're going to try to find the thing that we should be integrating, that's our p of x, and then multiply everything by that missing piece to create that product rule. So, number one, does that fit linear? And it's really close. We have a y to the first power, but we don't have the dy dx by itself. We want to make sure that that happens. So we're going to have to divide a lot of the times to make that work. So let's divide everything by 2x. If we do that, so dividing everything by 2 over x, dividing everything by 2x gives us 1 over 2x. We got our y. Then before we do anything else, we're going to simplify. So if we can simplify this side at least, then dy dx, that looks really good. That's by itself. We have plus 1 over 2x, no problem. That's our p. We have our y. On the right-hand side, we would get 5 over the square root of x. I know that's kind of improper to write that, but I'm going to leave it there because chances are that's going to simplify whenever we find our row of x and start multiplying. So now that's linear. That's a first order differential equation with derivative of y. Some function of x times y to the first power equals some function of x. No problem. Identify your p of x right now. Right now, we're going to integrate that to find the exponent of rho of x. That 1/2 right here, you can pull that out. So we're going to get e to the ln of x, sure, but we have a 1/2 there. So the derivative of this would give us, let's see, 1 over x times 1/2, that's 1 over 2x. Remember that you can do this. Or maybe make it a little more sense for you. Well, what we also want to do is we want to get rid of that e and ln, but in order to do so, we've got to move that exponent, or this coefficient as an exponent. So e to the ln of x to the 1/2 power, that gives us just x to the 1/2. X to the 1/2 is the square root of x. That's what we're going to multiply by. So we take everything and we multiply both sides, so every single term, by the square root of x and by the square root of x and by the square root of x. And we get this whole square root of x dy dx, no problem. Plus, if we simplify that, we're going to have 1 over 2 square root of x equals just 5. That's gone. Don't worry too much about what this looks like. It's not super important right now because all this has to be is the derivative of that piece. If you think of that as x to the 1/2 power, you move down the 1/2, oh, that's over 2. You subtract 1 from the exponent, that's x to the negative 1/2. Oh, that's 1 over 2 square root of x. That's all it's got to be. That's how you check your work. Now, the rest of it is so cool. This right here is the result of some sort of product rule. Let's write that product. The product is always, you left that piece alone when you took a derivative. You left this piece alone when you took a derivative. Just mash them together. On the right-hand side, you just have 5. If we integrate both sides with respect to x, then we get square root of xy equals 5x plus c. And let's just multiply everything by, divide everything by x to the 1/2. Or multiply everything by x to the negative 1/2. Either way, you're going to get y equals 5x plus c times x to the negative 1/2. If you distribute that, 1 minus 1/2 is just 1/2. And then we'd have c times, so the arbitrary constant times x to the negative 1/2. If you want to write it a little bit differently, I suppose you can. This would not be a big deal to write it like that, but you could write this as 5 square root x plus c over square root x. And you can rationalize the denominator, but if you see that, you could get that one as well. Okay, next one. I'd recommend you give it a try, at least the setup. See, that's an awkward looking 9, but that's supposed to be a 9. If you just try to at least set this up as linear, take a couple seconds and do that. So you'll notice it's not right now. You should make it fit. See if you can. Of course, for us, that means we're going to divide everything by 2x. When you're dividing everything by 2x, What I want you to do with your second term is group all of your coefficients, constants, whatever you want to call those, and your x's, group that together and just put y off to the right-hand side. So I want to see this as 3 over 2x times y. The reason why we're doing that, we're about to multiply, but that right there, that is going to be the piece of this product rule you didn't take the derivative of, so I want you to separate that and not even worry about it. On the right-hand side, we have 9x squared over 2. Now we're going to find the missing piece to multiply by to create this as the result of some sort of product rule. Well, write out what your p of x is. P of x is always the piece in front of the y. That's why we group it like that. That's why I just said that. So that you're not looking a lot of different places. You've grouped everything together and then you have your y out back. This right here is your p of x. When you take the integral of that, that becomes the exponent of your e to the rho, the e to some function of x. That becomes, as an integral, that function. Just like we did before, you can pull that negative 3/2 out. So we'd have negative 3/2 out in front of the integral, then 1 over x. So that's ln x. So e to the negative 3/2, that's your constant you pull out, ln x. Cool, let's move that as an exponent. So we have e to the ln x to the negative 3/2 power. E and ln are gone. That is what we have to multiply all three of those terms by in order to create the result of some sort of product rule. So let's do that. Let's multiply everything by x to the negative 3/2. Let's simplify where we can. So if we simplify, oh man, x to the negative 3/2, that looks fine. I don't gotta simplify that. You might even be wondering, why in the world do we simplify? Because don't you just know you're going to take this times y? Hello? You are, but you also want to check your work, don't you, to make sure you're not doing something that's just irrelevant. Also on the right-hand side, you're certainly going to want to simplify that. So we have our minus, we have our 3/2, and then if that's a negative 1, this would be x to the negative 5/2. Let's see if that works. Just to double check. Is the derivative of this equal to this piece? Again, that's why we group our x's together and the y off to the right so we can check our work nicely. The derivative would be bring down the negative 3/2, got it. Subtract 1 from that, hey, done. On the right-hand side, let's see, 4/2 must that be 1/2, 9/2 x to the 1/2. Since we've completed that product rule, or the result of a product rule, we can now really easily write out what the product was. The product rule always takes one piece and doesn't take a derivative of it in one term, and another piece that you don't take a derivative of in the second term. So we have to just group our rho of x and our y together. Done. Right-hand side, 9/2 x to the 1/2. And now we can take an integral of both sides with respect to x. I hope you're seeing that these don't have to take a long time. They take a long time when you don't understand them. And you go, where are these pieces coming from? What am I actually doing? How in the world do you get from here to here? It's just a result of a product rule. Look for the pieces that you wouldn't be taking a derivative of from your product. That creates your product. Your integral with respect to dx should be very manageable. On the left-hand side, nothing happens. You're undoing a derivative with the integral. You get x to the negative 3/2 y. On the right-hand side, yeah, a little bit more work. That's where actually most of your work is going to come from here. Let's see, we add. So x to the 3/2. over 3/2, that's going to give us 3. Right-hand side, 2's are gone, 9 divided by 3 is 3. Don't forget that plus c. But then all we have to do after that is multiply both sides by x to the positive 3/2. That's going to kill this off. That's going, actually, going to kill that off too. Oh, no, it's not. But it's going to get multiplied there. So let's try that. If we multiply both sides, we would have x to the 3/2 and x to the 3/2 right there. This is gone. You're going to get y. On the right-hand side, well, what do you do when you multiply exponents together? So you add them. So 3/2 plus 3/2 is 6/2. That would be 3. So distributing this is going to give us 3x cubed plus c x to the 3/2. And that's about as good as we can get without an initial condition. Also be aware that a lot of times you'll have a y without an x at the very end. They'll say, yeah, don't forget that you're solving this explicitly right now as a function of x. So if you see that, that's where that's coming from. It's just telling you what that is. I'll be back with a couple more in just a minute. Let's do a couple more. So first one, we have a linear. Do you see it's linear? Can you see that that fits perfectly to exactly what we're trying to do here? You got a first derivative. You got plus y, you have a function of x, there's no other y's, y's the first power, it looks pretty good. This is fitting our linear first order differential equation perfectly. Let's find our p. So p of x is that piece that's right in front of y. In this case, p of x is just 1. Rho of x says you're going to do the integral of whatever that p is to find the exponent of an exponential. So in our case, we are just going to get e to the x. That right there is that piece that you're going to multiply by to complete your product rule. And yeah, I'm trying to kind of brainwash you right now. I'm saying the same thing over and over and over again because we have lots of techniques and lots of stuff, and it's easy to forget this stuff. I'm trying to get you used to the format and used to what it is you're doing. Because if you understand what it is and why it works, you're less likely to make a mistake and less likely to forget it. So we're trying to complete a product rule by finding something that repeats and something that when I take a derivative of the exponent, it's going to give us back the thing that's multiplied onto y. So let's multiply. That's dy dx plus y equals e to the x. And we're going to multiply everything times e to the x. Now we're going to double check our work. Okay, well, is the derivative of this thing equal to the piece that's being multiplied to y? Yes. And now we can keep on going. We know that we've completed the result of a product rule with respect to x implicitly. The result of the product rule says you left the first one alone, you left the second one alone in the second term. On the right-hand side, you have, let's see, e to the x times e to the x, that's e to the x squared, multiply exponents, e to the 2x. Now we're ready to do an integral. Because we know this was the result of a product rule of a derivative with respect to x, we do an integral with respect to x. Right-hand side, no problem. It's a u sub. If you need to show a u sub, we'd have u equals 2x. Excuse me. If you take the derivative, that's 1/2. So we'd have 1/2 e to the 2u. And sure enough, the derivative of this gives us e to the 2x times 2, which would get rid of that 1/2, plus c. On the right-hand side, really nothing happens. If we divide everything by e to the x, we would get 1/2 e to the, now imagine this, you're dividing by e to the x. This is e to the x squared. So you're going to get e to the x plus c e to the negative x, or c over e to the x. If you have initial conditions, you'd want to plug them in here to be a little bit easier to solve. So when you get down to undoing your derivatives, if we wanted to plug that in there, like y of 0 equals 1, you'd want to do it here. So x would equal 0, y would equal 1, so that would be, c would be 1/2. So if you want to try that on your own, we'd have e to the 0 times 1. You can see this is 1. Subtract 1/2, you get c equals 1/2. And we can leave it just like that. The next one, I'm not actually going to do for you because I want you to look at what's going on. To do this with as a linear differential equation would require a lot of work. That's not how I want you to think. So yeah, this can possibly be in your do this linear. And if you have to, you have to. And I'll talk about that for a second, I suppose. But do you see that that is separable? Why in the world would we make this harder than it is? If you can make this 1 over 1 minus y dy equals cosine x dx, which you obviously can, and integrate. That's pretty darn easy. That was not a lot of work, and I'll show you what linear would require of you, and you can do it on your own. See, actually, I would encourage that. See if you can do it on your own in just a minute. So ln, that would be negative sine x minus c. Little recap of separable equations, I suppose. 1 minus y would equal, remember we'd have e to both sides. We'd have e to the negative c times e to the negative sine x. I drop my absolute value, need a plus and minus. We wrap this whole thing up into a gigantic c. I'd want to plug in my initial condition here. So if we plug that in, then 1 minus 2 equals c e to the negative sine of pi. Sine of pi is 0. E to the 0 is 1. 1 minus 2 is negative 1. C equals negative 1. And when we put that back up here, we would get one minus y equals negative 1 e to the negative sine x. Let's subtract 1. And if you divide everything by a negative, we get 1 plus e to the negative sine x. That's not that bad. That wasn't a whole lot of work. If we try to do it differently, if we try to do it linear, I want you to see the difference here. So that was separable. That's fine. That gave us the right answer. This is the same exact answer. If you had to do this linear, you'd have to distribute we'd have to get the cosine xy on the opposite side. So we'd have to group our y's together, basically. Then you'd have to say, okay, well, what's my p? My p is cosine x. My rho would be e to the integral cosine x. That's sine x, and we would multiply it every single, on both sides, every single term. So we'd have, it's going to do it kind of quickly, we'd have e to the sine x, and then e to the sine x, and most importantly, e to the sine x. On the left-hand side, this is not a problem. This would say, okay, yeah, you're going to have a derivative with respect to x of e to the sine x y, which of course the derivative of e to the sine x gives you cosine x e to the sine x, not a problem. Well, on the right-hand side, you're going to have to take the integral of cosine x e to the sine x. This side, easy, derivative's gone. This side, take an integral with respect to x. We get e to the sine x y equals, Well, that's a U sub, and you can see already there's a lot more work here. That already introduces something that I don't really want to have to deal with if I don't have to deal with it. So you take a U equals sine x. I completely lied to you, by the way, so I'm not going to do this, and I'm totally doing it because I can't help it. Cosine x dx, so e to the u would be e to the sine x. And you can see that that's the derivative of this gives you that right there, so we get cosine x e to the sine x plus c. And we would plug in our pi for x and our 2 for y, and we would get that this would equal, let's see, 1 times 2 minus 1. Let's see, c would equal 1. So c would equal 1 here. That tells us that, I know we're kind of running into the problem, we would get, I'm going to do two things. I'm going to tell you that c is 1. I'm also going to tell you that to get rid of e to the sine x, you'd multiply everything by e to the negative sine x. That would give you y, that would give you 1, that would give you 1 times e to the negative sine x. And that's exactly what that is. Which way is easier? The way that makes sense. In this case, both of them work, but if something fits a simpler technique or something fits without having to modify it, you should probably use that technique. Right here, there's no reason why we want to do anything else besides linear. Right here, there's no reason why we should do anything else besides separable. That was easier. I think that was easier to get to. Here, I had to shortcut this a lot, but it is possible to make that into a linear. So whatever technique makes sense to you, but generally speaking, it's the one you don't have to do as much work with. The one that you don't have to modify to make it fit. Sometimes there's exceptions to that, but in general, that's what you're looking for. So let's try two more. Honestly, I would like you to try that one on your own, at least as far as identifying whether or not you have a linear first order differential equation. That one's weird, so I'll talk about that one together. But see if you can see if that's linear. If it is, can you identify p? Can you do that? Can you see if you can do the integral of p and put that as an exponent on e to some function of x for rho? Can you multiply everything by that? Give that a try. Pause the video if you can. Just see if you can do it. If not, no big deal. You're still learning it. So together, yeah, that's linear. That's first order derivative of y plus some function of x times y to the first power equals something that doesn't have y's in it. That's what we're talking about. Now that we have it in proper form, we find p of x. Well, p of x is the factor that's attached to y. That's cotangent. The thing that's going to complete our result of a product rule is always an exponential, and the exponent is an integral of p of x. And we talked about that at length on why that works that way. So I would use your table, use your integration table, use whatever it takes to do that integral quickly. That is ln of absolute value of sine x. So if that is ln absolute value sine x, well then e, ln are gone, and we just get that this is equal to sine x. And that's what we're going to be multiplying all three terms by. So we'll have sine x dy dx plus y times cotangent x times sine x equals cosine times sine x. Now, we do like to simplify quite a bit because right now you go, hey, the derivative of sine x is not this. Yeah, that's true. The derivative of sine x is cosine x. So let's see if that makes cosine x. Remember, cotangent is cosine over sine. Well, that gives you just cosine x. So when we simplify, things are a little bit more apparent to us. So sine x dy dx, no problems. Plus, well, we could have cosine x times y equals sine x cosine x. Derivative of this gives us that, and that's how you check this. That's how the product rule works. So this came from some derivative with respect to x of a product rule where we left the first term alone on the first factor alone on the first term, the second factor alone on the second term. And that gave us an equation, a differential equation, where the right side is exactly that. Now when we integrate with respect to x, because that's what we took a derivative with, these are gone. We get sine x times y. On the right-hand side, yeah, you're probably going to have to use a u sub. U equals, I would pick u equals sine x. That way the derivative of sine x is cosine x. So we would just get u squared over 2, or 1/2 u squared. So that would be 1/2 sine squared x plus c. And if we, well, let's see, we'd have to divide, wouldn't we? So divide by sine of x. Hopefully you caught that. U would equal sine du. Let's take the derivative of that. That's cosine x dx. So this would be an integral of u du. This whole thing is du. That gives us the 1/2 u squared, and then you just put sine right back in there. That's how I'm getting that. I'm just doing a lot of it in my head. I probably shouldn't have done that, sorry. So we'd have 1/2 sine squared x plus c. If we divide everything by sine x, well, we get 1/2 sine x, because you divided, sine squared divided by sine. But you'd also get plus c over sine x. So dividing everything by sine x. Let's just make that better. We know that 1 over sine x is cosecant. So let's write that as cosecant. Hopefully there's a little review of trigonometry for you too. And that's what we want to see. So we did our basic integral. Again, most of the work is done on the right-hand side. Left-hand side just kind of plays along. You have a set technique for that. And then we solve for y. So divided by sine x squared divided by sine x gives sine x. C divided by sine x gives us cosecant x. That's the idea. So the next one, that thing doesn't look anything like how we want it to be. You go, yeah, all right, well, I mean, at least it's got a first-order derivative, first-order differential equation, but it's not separable. You got 4 terms up there. I don't see how I'm going to be able to get, I have 2 y's. What in the world's going on with that? If you're going to try to make this linear and you have the y in 2 places, you're going to have to factor. So let's try to factor this. And since there's 4 terms, maybe it clicks and we go, oh, let's see if we can factor by grouping. Why don't you try that now? See if you remember how to factor by grouping. Factor by grouping, groups the first 2 and says, what can you factor out of that as far as a GCF? Nothing. Nothing means 1. Grouping always brings down your middle term, groups the last 2 and says, what can you factor out of that as far as a GCF? Y. And if you have 2 terms with the same factor, you can keep on going. Factor 1 plus x, what remains is 1 plus y. Let me ask you, is there any way that you wouldn't do that with separable equations? Why wouldn't you do that with separable equations? You can divide both sides by 1 plus y, leave the 1 plus x where it is, and move the dx. So I would certainly do it that way. Of course, if you're trying to do by linear, you don't make it that far. So this right here, this would be done, if it's possible, you do it by separable equations. I'm not going to go through that. I'm going to go back 1 step. That's how I would recommend trying it. Go, yep, that's separable. See if you can move 1 over 1 plus y, 1 over 1 plus x, and integrate both sides. To do linear, you gotta leave it there. Why? Well, I told you that you need some function of x times y. When we factored this, we've got y times that function. This is kind of irrelevant. Let's move this to the left-hand side. Let's group our y's. Okay, if we do that, we'd have dy dx. We'd subtract 1 plus x times the y. On the right-hand side, we still have 1 plus x. Well, now that we've written this as linear, so hopefully you've learned that on some of these, there's more than one technique available. That happens quite a bit. I would have picked separable at least to try it. If we run into a problem, then we go back and do linear. Since we're practicing linear, I'm going to show you where that happens. So I would have tried separable. If that didn't work, then I come back here and go, okay, let's try our linear. I can go back one step and say, yep, I can subtract the thing that has our only y. On the left-hand side, group our dy dx and our y term. On the right-hand side, we have an x term. And then we can identify what p of x is. P of x is always the piece that's right in front of our y. Rho of x says you're going to get this exponential where the exponent is the integral of your p of x. Because when you take a derivative of that, it'll give you back your p of x. So if we take the integral of that, it looks really nasty, but we have e to the negative x plus 1/2 x squared. Integral of 1 is x, integral of x is x squared over 2. So 1/2 x squared, and we have that negative out front. Unfortunately, that is what we have to multiply all of this crap by. Why did I just pick separable? So I left that big spot for what we're about to multiply by. So I'm going to multiply everything by my row. So e to the negative x plus 1/2 x squared and e to the negative x plus 1/2 x squared and e to the negative x plus 1/2 x squared. Now the left-hand side is always very nice. All you have to do is check it. Is the derivative of this piece equal to this piece? Well, the derivative here would be 1 plus x, and then it has a negative, so yep, that works. So we can take all of that and say, hey, that's the result of some product rule where I had this piece times this piece, and we know it's got to equal this piece. Then when we take an integral, the left-hand side's basically done for us, no big deal. On the right-hand side, you're going to need a u sub. So when we do a u sub and we say, let's just let u equal the inside, so the nasty part. Then we see that du equals 1. We take the derivative. Derivative of x is 1. Derivative of 1/2 x squared gives us x. And we go, okay, du equals 1 plus x dx. That's this whole piece. But just notice, we did not include the negative with that choice of u. So this would equal the integral of e to the negative u du. Be careful with your signs. Be careful with that. Left-hand side, we're going to leave that alone for just a minute. Right-hand side, we get negative e to the negative u plus c, but we know what u is. Negative exact same exponent. this is the time where you would want to find your c. So if we plug that in, we would have, this gives us 0. So 0 plus 0, e to the 0 is 1. This gives us 0, so the whole left side is 0. On the right-hand side, you would have 0 plus 0, that's 0. E to the 0 is 1, that's negative 1. So c equals 1. 0 equals negative 1 plus c equals 1. And let's go ahead and let's put that in there. Because now what we're going to multiply by, and you might have been wondering, why am I leaving that negative out there? Well, this happens a lot. It happens that when you get to the end or get to your substitution, these things work nicer without distributing that. We multiply everything by e to the positive version of this. That would create 1, so just y, negative 1, and then e to the positive exponent there. So multiply everything by e to the positive exponent. Gone. This whole thing is gone times negative 1, so negative 1, plus 1 times the positive exponent version. And that's about as good as we can get on that one. You might want to write that in different order. So you could have e to the x plus 1/2 x squared and then plus or minus 1 at the end. No big deal. But that's the idea. Is it's this all this stuff works, but sometimes you kind of want to check what format of what technique would work best. In this case, I would have certainly tried separable equations first. Okay, let's try another one. This has some more advanced ideas on what we can do. So let's try to make it fit. We're going to go quickly through it. I told you we're going to get more advanced. We're going to go quickly because the technique should be there. So number 1, does it fit? No. Make it fit linear if we can. So let's divide everything by x. We're also going to want to make sure that we group our x's in front of our y because that's going to be our p. And we're going to simplify. Well, 2x over x gives us 2 minus 3 over x. Let's treat that as our p equals 4x cubed. Then when we find our p and do the integral of that, it's a little bit more manageable than something ridiculous like this. That would be kind of difficult to do. We'd be doing this anyway. So p of x is 2 minus 3 over x. Rho of x says take your exponential, do an integral of p of x. See what that does. 2 gives us 2x minus 3 ln x. So integral of 2 is 2x minus integral of 3 over x gives us 3 ln x. We know we can move that exponent up. And we can also separate this. So we could do e to the 2x times e to the negative, or sorry, yeah, I guess so. No. E to the negative ln of x cubed. But we can also move this as this. Make that an exponent. You can multiply. You're going to get x to the negative 3rd power. We could have done it right from here too. You can see the same thing. Move the negative 3 up and add. That's fine too. It doesn't really matter. We get e to the 2x equals e to the ln of x to the negative 3. Those times, those are gone. We have e to the 2x over x cubed. Y over x to the negative 3rd power gives us 1 over x cubed. So e to the 2x times x to the negative 3rd power gives us e to the 2x over x cubed. That's our rho. Let's take that and let's multiply. We now know that we're completing that product rule on a product when we take a derivative. Lots of things are going to simplify on the right-hand side. So we have x cubed is completely gone. We're just going to get 4 e to the 2x. We would double check this, but man, that's a product rule with a negative. So if you distribute this and you figured that out, the derivative of this is that thing. That's crazy, but you should work that out. We know that this is the result of a product rule. A product rule of a derivative with respect to x where we took the first factor and left it alone for the first term, the second factor and left it alone for the second term. And if we do an integral on both sides, I hope I'm not going too fast for you. I hope that made sense. It's the same technique. This is you get a little bit more advanced. So the p can look funny. That sounded funny. When we do an integral of that, don't forget that you can split up fractions. Don't forget that we have an e to these things. You can split up that e as a product of e to whatever those things or those terms are. And we know that negatives and coefficients move as exponents. We can simplify e to ln, no problem. That's our row. That, I don't care what you have, that's what you're multiplying every single piece by, and that's what we've done. We've simplified where we could, and we know that this is the result of the product rule, write the product. After that, we do our integral, we get e to the 2x over x cubed times y equals, use a u sub if you like. This is going to be 2e to the 2x. And we know that because when you take a derivative of this, we would get back the exponential times 2 on that 2. So that would give us that 4 plus c. And lastly, all we need to do is solve for y. So we'd multiply everything by e to the negative 2x or divide everything by e to the 2x. So this, and that's going to get e to the negative 2x. And we'd also multiply by x cubed. So basically multiply by the reciprocal of this. So y would equal, we'd still have a 2, but you'd no longer have an e to the 2x when you distribute. You just have x cubed. But we're going to get both of them on the c. That's about as good as we can do on that problem. Okay, last one, and I just want to talk about this because the setup is so strange. Whenever you get something that looks really weird, like, man, it's almost linear, but there's a y over here, you're going to have to factor. Do the factoring first before you divide. It'll be a lot easier on you. So what I mean by that, and this is just a setup, I'm going to do about a quarter of the problem, and then you can try it on your own. We'd want to get our y's on the same side. So we'd subtract that. And it is okay to get 0. In fact, in this problem, after you figure out the product, to get the product rule, you're going to be integrating the right side. It's going to be 0. No matter what you multiply by. Do you see that? No matter what you multiply by, you're going to get 0. So the integral of 0 just gives you 0, or actually gives you c, a constant, plus c. So don't worry about that. Get your y's together and factor. And then you can divide everything by x. So when you divide by x, we get dy dx. We get 1 minus 3x over x. And we would still get 0. It's okay to divide 0 by x. Split that up just like the previous problem, and then you're going to be all set. So we would get 1 over x minus 3. It's going to look so similar to the last problem. Your p of x is this. You take the integral of that. You have an ln x. You should see that. That will cancel. You'll get just x minus 3x. So you have e to negative 3x. Multiply all 3 spots. Just don't forget that when you do an integral to the right-hand side, this is for you. When you do integral to the right-hand side, you're going to get a constant. That's where your c is. That's about it. I hope this makes sense that when you have 2 y's, you're going to have to factor. All right, guys, I hope the video makes sense. I'll see you for the next one. Okay, just kidding. I couldn't leave it. I just had to do it. So anyway, I worked it out, and this is just the answers for you. So if that's your P, I integrated the P, I separated from my row, made it a lot nicer. I multiplied everything here and here and here, which still gave me a 0. I created my product. It's very easy to do. Just take this piece, put a y next to it. That's your product. Integrated both sides. Integral of 0 gives you c, and then solve for y. So that's what you should be getting. That's what you should have gotten. All right, now let's see the next video.